but they are a lot of fun. And thank you all for joining us. If you're watching, we're going to get started here in just a sec. While you're watching, if you got any comments, questions, please let us know. I see a lot of people are joining us here. Eric, Aaron Coble, thanks, man, for joining us. Says it looks great. Sean, Frank, thank you. Ron McLaughlin, sorry, I hope I'm saying that right. Jeff Elliott, David Lopez. Is Ron one of your guys?
Yep.
Mike
we got
Gable.
a lot of our guys coming in.
Awesome. Thank you guys so much for joining us. And please ask questions. Andrew's asking about the PE numbers. We'll talk about that here in just a second. And we're going to get started here just in a few seconds here. So let me see my next steps. I'm going to go ahead and do one of these deals. Talk about this. Okay, so we're going to go ahead and get started. So Tony Mormino with Insight Partners. If you see me kind of moving around here, I'm jumping around, changing some screens around. So thank you for watching live today. We are live streaming on LinkedIn and YouTube, which is just tons of fun. We so appreciate y'all's support. We've been doing this now for about 6 months, and it's been just amazing. And we love that we're getting a lot of support on it. So thank you so much. Thank you so much for being here live and watching. And if you're watching a recording of this, which is the majority of people who watch these come back and watch the recording. So if you're watching that, thank you so much. We appreciate you being here for that too. Excuse me just a second. Okay, so if you want to watch the recording, the best place to do that is on our YouTube channel, which is Insight Partners HVAC TV. And I will post a link to that in the comments, and you can go check that out anytime and watch not just this, but all of our recordings, which is really cool. And this particular episode, we're going to put on our new podcast. So we have a podcast now called the Engineers HVAC Podcast. And we launched this thing about, 4 or 5 weeks ago. We've got 5 episodes on there. We've had over 450 downloads. So greatly appreciate the support. We're going to start putting more of these out there. So if you want to listen to this on the ride home, re-listen to it sometime, you could check out the podcast. I'll put links to the podcast in the comments as well. So at Insight Partners, we are an HVAC solutions provider with a nationwide network of experts committed to our local partners' success. And we have one of those experts here today, and our local partners are you guys. So thank you so much for watching. And they've prepared this amazing presentation on HVAC Acoustics 101. And our partners that I'm referring to today is Bosch Thermotechnology. So we appreciate you guys for all the hard work you've done. We've done a few rehearsals on this, and I've seen the presentation. It's really good. It's really a great, if you've been around a while like I have, it's a great refresher. And if you're new, it's a great way to learn about a very important topic of acoustics. So for PDH credits or PE credits, we're going to post a link to a short quiz at the end of this video. So if you're watching live, we'll post it near the end. You can click on it. You can go do it. If you want to come back and do it later, that's fine too. Just keep a hold of that link. And you could always email me or message me on LinkedIn, and I'll be glad to help with that as well. So quick introduction. So I'm Tony Mormino. I'm the Technical Sales and Marketing Director for Insight Partners, and we're a rep firm in North Carolina, South Carolina, Florida, and Georgia, HVAC rep firm. And I've been in the industry for about 25 years now, engineering degree from University of Florida. And I've been with Insight Partners for a couple of years. I was with Train for a bunch of years. I was with my own private rep firm for a bunch of years. And now I'm with Insight Partners for the last couple of years. And the last 6 months or so in my new role as marketing director, which has been a lot of fun. It allows me to do a lot of stuff like I'm doing today, which is super, super fun, and get to share this stuff with you guys. And I am in Asheville, North Carolina today, and I will pass it over to Phil and Shaz, where they'll do a little introduction on themselves. Phil, you want to tell us a little bit about your experience?
Thank you, Tony. My name is Phil Raines. I'm an application engineer with Bosch. I've been with Bosch now almost 11 years. I've also worked for Carrier and Amana in my life. I have over 53 years of experience in HVAC. I went to night school for engineering for 17 years. I had my own company for a quarter century. It's not much in HVAC that I haven't touched. I don't know whether I did it right, but I've done it. So it's a pleasure to be here. Thank you.
Thank you, Phil.
Yeah. Thank you, Tony, for introducing us as well. Happy to be here and happy to take part in this discussion. My name is Shaz Syed. I'm the Engineering Applications and Training Manager here at Bosch Thermal Technology. Been with Bosch for about 3 years, trying to support our commercial group in water source heat pump and commercial boiler channel, originally from California. So, yeah, ready to talk about a very interesting and a unique topic today with you about acoustics and HVAC.
Excellent. All right. Thanks, guys, for that introduction. I'm looking forward to it. So, okay. So this starts. I'm going to start the actual CEU presentation. So, Tony Mormino, welcome to the CEU course, Acoustics and HVAC, presented by Phil Raines and Shaz Syed, and associated with Bosch Thermal Technologies North America. So, in this presentation, we're going to explore the importance of acoustic in HVAC and how it relates to the to air distribution in the system. So, please post any comments in the comment section, any questions in the comment section. We want this to be engaging. What we will probably do is wait till the end to answer any questions. So please stick around and we'll glad to do that. So noise is a topic which plays a major role in HVAC systems, yet it is a topic which either is misunderstood or, some of the terms get constantly confused. And I say that for myself too, as well as everybody else in the industry. So some examples of those terms are sound unit dB, dBA versus dBA, sound pressure, sound power, AHRI 260 2011 versus AHRI 260 2017, just to name a few of the things we get mixed up, and that includes me too. And a lot of times I need a refresher, which is what we're doing today for me. So the one thing we can all agree on, that too much sound or unwanted sound can create unpleasant living or working conditions, and usually the end user is willing to pay a little bit more on the front end or even on the back end if you're correcting an issue to make these issues go away. So in this course, we're going to go back to the basics of sound. Excuse me a second. Back to the basics of sound, where we'll define commonly used terms, review the concepts of acoustics and frequency, understand the difference between sound pressure and sound power, and review how sound is measured in HVAC units. We'll wrap up with some case studies, which will help to determine how room construction and unit construction can affect the NC noise criteria rating of a given room. So with that being said, I will turn it over to, I think Phil is going first, and he's going to talk about, let's see, what is sound? So Phil, take it away.
All right. Thank you, Tony. Thank you, everyone. So when we talk about what is sound, going back to the basics, sound is basically any pressure variation that the ear can detect. These pressure variations are caused by a vibrating object or surface or by turbulent air, gas, or water. The range of hearing for the human ear is extremely broad. We can actually hear sounds as low as a blade of grass blowing in the wind to the roar of a jet engine as it takes off. Sound is an active part of our everyday lives. Sound can be pleasant and provide comfort and relaxation, or it can also be considered a nuisance or even a disturbance. Noise, on the other hand, is any annoying or unwanted sound. What differentiates a noise from a sound is, of course, subjective, but it's often due to its volume or its tonal qualities.
Okay, thank you, Phil.
Yeah, also like to kind of lay out some of these definitions before we get into our basically panel discussion, just to make sure that everybody is familiar with some of these terms that will be thrown around. So, just as a refresher, or if you don't know, getting you familiar with those. So we would like to lay the foundation of how the sound units are measured. A pressure variation in a sound wave can be measured in micropascals to determine its loudness. The greater the pressure variation that is in the sound wave, the louder it will be. The micropascal is an actual physical measurement of the pressure variation in the sound wave. The weakest sound detectable by the human ear is actually 20 micropascals. So to put this into perspective, a pressure change at this level causes the eardrum to displace less than diameter of a hydrogen molecule. At the same time, the ear can also withstand pressure changes of more than 1,000,000 times this lower threshold. This type of measurement will result in a rather large and awkward scale. So to avoid this, another scale is used, which is called the decibel or dB scale. Compared to the micropascal, The decibel scale gives a much better representation of the way humans perceive relative loudness. This is because the ear does not react proportionally to changes in volume, but does so according to a logarithmic scale. So we note that while the micropascal scale is a little linear measurement of sound pressure, the decibel scale is actually more compressed and focuses specifically on the human range of hearing. To demonstrate this, we will be using the interaction screen a little bit to demonstrate some of the sound volume. So as I mentioned, lowest threshold of hearing for a human ear is about 10 dB or 20 micropascals. Then we have basically, a whisper quiet bedroom where there's barely any noise. So that will be about 40 dB. So that's kind of like the baseline. But now let's look at the conversational scale on this side. And let me actually click on that. There we go. So the conversational speech, that's about 70 dBs on a regular basis. Now we look at the residential road, which is about 80 dB. Then we'll look at the underground train, which is now 100 dB. Notice how the sound is actually sounding twice or 3 times or 4 times as loud as we're moving up the scale. Now car horn, which is 120 dB, and a pneumatic drill, and beware, it's going to be loud, 130 dB. So basically a threshold of hearing for a human ear. On the left side, you're seeing the pascals, and on the right side, you're seeing the dB scale on our side. Some couple of other definitions that we'd like to kind of get you guys familiar with, or some of the units. A-weighted sound is corrected for the sensitivity of the human ear, with most emphasis placed on the frequency ranging from 1,000 Hertz to 4,000 Hertz, where humans are most sensitive to the hearing loss. A-weighted sound criteria is commonly used in outdoor sound evaluation and is often incorporated into city building codes when referencing the maximum acceptable sound pressure level at the property line. It is popular because it is a single number that most sound meters will include. Another one, noise NC criteria, which is NC or noise criteria. It is used as a standard describing or expressing the complexity of relative loudness of a space within a range of frequencies, where the acoustical environment greatly influences the amplitude and frequencies heard by the occupant. So simply stated, NC is a sound pressure at each octave band, which we'll talk about in a minute, with an NC of 35 referenced as the most common noise level specified for the HVAC equipment. NC curve, as shown here, were developed to represent lines of equal hearing perception in all octave bands and at various sound levels. These NC curves allows a single number rating of the sound spectrum, and the sound pressure at each octave band must be below that NC curve. An NC between 35 and 45 is best for speech privacy and in offices and various different environments. And we'll talk a lot more detail into this as we go on. So some of these definitions to just kind of clear out the way so you guys are familiar when we talk about them.
Great. Thank you, Shaz. And to your surprise, I know no one could hear those examples. So we rehearsed this 4 times. Half the time they worked, half the time they didn't. We took a risk. We rolled the dice and went for it, and you sure couldn't hear them. So no big deal. I think everybody knows what a drill sounds like. So anyway, no worries. We'll figure it out. It's not on our end. It's some kind of glitch on well, maybe it is. I don't know. It seems to be some kind of glitch on live streaming and sharing your screen. But anyway, we went for it. We failed. Okay, so moving forward. All right, so we're going to do a little question and answer thing here. We got 12 quick questions. So the first question is, when will a person start to notice a difference in sound? And Shaz is going to take us home with that one, or start us off with that one.
Absolutely. So when we are talking about perception of sound and when will you actually notice a sound difference, there are some important things to remember about that measurement. So it's a logarithmic scale, how sound is measured, as we talked about in previous definition that we were reviewing. So a change of 3 decibel is barely noticeable. So 1 to 3 decibels, it barely makes any impact on a human hearing. So they will really not notice a difference on 2 equipment playing at a difference. But right after that, the human ear starts to notice a change in the volume. So at 5 dB, the sound difference is clearly noticeable. All right, and from 5 dB onwards, a human ear can clearly detect that this machinery, equipment, or whatever is either relatively louder or relatively quieter. And at 10 dB, it's perceived to be twice as loud. So we can really tell that this is really significantly quieter or significantly louder.
Okay.
Hope that clears out. Yep.
Very good, Chaz. Thank you. All right. Question 2 of 12. How do we add different sources of sound?
Yep. So because, again, the decibel scale is logarithmic, the addition of sound levels cannot be done directly. So we will look at the concept of adding the sounds. And let's revisit this as well. We will visit the 3 sound sources that we discussed earlier. Again, nobody could hear, but we have a conversation, quiet bedroom, and a residential room, 70 dB, 40 dB, and 80 dB. We will not be adding them traditionally. They will be added using the formula shown below, logarithmically, and the total. When you have all 3 of sound sources at various different sound level, they will add up to about 80 dB in this case. Also notice the residential road was the 80 dB mark. So anytime you have a 10 dB difference or larger, generally the loudest sound source will be basically the dominant one, and that's how loud the sound will be altogether.
Okay, thank you very much. Logarithmic. Okay, so the next question.
Yeah.
We're going to talk 3 of 12. So now let's talk about frequency. What is the role of frequency when measuring sound?
Yep. And so in this slide, also has some sounds, cool, music to play, but I guess that's not going to happen. But let's talk about frequency. Frequency, which is actually measured in hertz, is the number of pressure variations that occur per second. In a sound wave, the sound frequency produces a distinctive tone. This is why a flute, which has a high frequency, and a bass drum, which has a low frequency, sound so different. The range of human hearing is anywhere from 20 hertz all the way up to 20,000 hertz. The human ear, though, is most sensitive between 2,000 hertz and 5,000 hertz. Want to again experiment, but just for you, I think we can all imagine what any of these music instruments will sound like. Bass drum, again, really high on bass, but then as we moving up with tuba, clarinet, violin, flute, whistle, whistle being the most squeaky one. So you can just imagine as we turn up the frequency, you will start to notice the sound difference as well. And each will be perceived differently as well, and we'll talk about that.
Excellent. Thank you. In my experience in my career with acoustics, as far as like repairing or fixing a acoustical issue, is the lower frequencies are much harder to attenuate than the higher ones. A lot more mass is needed.
Yep.
Has been my experience. So thank you for that. I think we're on number 4. Mm-hmm. So question number 4, how do we perceive sound at different frequencies?
Oh, I'm sorry. All right, there we go. Sorry, I had a small glitch on this. Okay.
No problem.
All right, so perceived sound level. A phone, which is another unit, is a perceived loudness of a sound. A human sensitivity to sound is variable across the different frequencies. So 2 different tones may present in an identical sound pressure to a human ear. They may be psychoacoustically perceived as differing in the loudness. So to explain this point further, let's take a 60 phone curve, and I will use my laser pointer to kind of point that out on this chart. So 50, 60 phone curve. So at 60 hertz frequency, which is kind of just shown right here, 110 dB sound pressure level will be perceived as 60 phones. And at 1000 hertz frequency, which is right about here, a 65 dB sound pressure level, which is kind of right about here, will also be perceived as 60 phones, which will be just as loud. So it is an interesting concept to consider when we will look at, our, sound casing radiated sound discharge, casing radiated sound data and the ducted discharge sound data for the HVAC equipment later on. That how do we perceive various different frequencies and different sound pressure levels?
Okay, thank you very much. Shaz, you can go take a quick break. We're going to turn it over to Phil. And Phil's got like 155 years of experience in the HVAC business, so he's gonna he's gonna help us understand octave bands. So,
All right.
what's going on with these octave band things?
Thank you, Tony. Okay, when we're talking about understanding octave bands, although it's important for us to get an idea of how loud a particular product or a machine or anything is, it's also useful to know what frequency that device produces. So unlike a musical instrument which produces a specific note, any device such as a water source heat pump or even an air handler will simultaneously produce a vast variety of different frequencies. So for instance, if we have a blower fan, it might produce a lot of low frequency noise, and its motor will at the same time produce a very high frequency noise. So noise might be produced by airflow also through the duct discharge. So to derive frequency-specific test data, electronic filters are often used to isolate the noise occurring in the following frequency ranges. So note that each of the frequency bands center on a frequency which is double that of its predecessor. So a tone with a frequency that is twice that of another is said to be 1 octave higher. The frequency ranges that we analyze are therefore called octave bands because the contributions found in the octave 1 and octave 8 bands are often imperceptible in HVAC applications. So we discard the data found in these frequency ranges before we publish any results in any catalogs. But once the original sound has been separated into frequency bands, we can then measure the loudness of each one independently. Thank you, Tony.
All right, thank you very much. Clears that up. So question 6. So 6 of 12, halfway through. Thank you all so much for joining us and watching and sticking with us here. By the way, if you like what you see and hit the little like button, we would greatly appreciate it. So what are the differences between sound power and sound pressure? Extremely important to know the difference for sure. So take it away.
Yeah, and as you mentioned earlier, that's one of the more industry common, misperceptions as to when we're talking about sound power and sound pressure. So if you take away anything from this presentation or our discussion, is this topic. So sound power and sound pressure, these are often presented when discussing the acoustics for the building. Engineers must clearly distinguish and understand the difference between the sound pressure and sound power levels. AHRI definition is listed there, so I won't repeat that, but it is, in the simple layman term, sound power is the rate at which sound energy is emitted, radiated, reflected, or transmitted by a sound source per unit time, or basically what sound the equipment generates. Converted to sound pressure is then as it then propagates out of the room or space. For sound pressure, again, HRI definition is listed there, but in simple layman's term, it is what our ears will hear, which is a result of a sound source radiating sound energy into a specific acoustical environment. And it is measured at a specific location in decibels, and which we have already discussed previously. So to calculate the sound power and the sound pressure of the equipment, it is used along with the specific transfer formulas that define how the sound pressure is absorbed or reflected off the surfaces in the space. The conversion details are unique to the material used in the space, and when applied, results in an application-specific generated pressure level. So the greater the sound pressure, more energy is carried by that sound, and the louder the perception to that sound will become. So even though the sound power and sound pressure are both often expressed in decibel, there is no outright conversion between them, although we'll kind of allude to them a little bit. A constant sound power output will result in significantly different sound pressure levels when the source is placed in different environments. Uh, Also, I'd like to give you an example of the difference between sound pressure versus sound power. We will take an electric heater in a room, which is the power of that electric heater is about 5 kilowatts, and the temperature of the room is 70 degrees Fahrenheit. So in this case, the sound power of that equipment is 5 kilowatts. So that's our sound power equivalent. And then the sound pressure equivalent will be the temperature of that room. That temperature will vary depending on the size of the room, location, or characteristics of that room. Knowing the sound power levels for a piece of equipment will allow us a fair and direct comparison between various different unit sources, but will not, however, indicate whether the sound levels will be acceptable until the space in which they're being installed is defined. This means that actual space where the equipment is used has the same properties as the test conditions. The sound pressure level provided will not be what the occupant actually really experiences. So hopefully that topic actually makes sense.
That makes great sense, and I love the heater example, and I just love how happy that family is. Look at them just sitting there.
Yeah.
Beautiful. Must be enjoying that heater. Okay, so question 7. Before we go to this question, we're getting tons of questions in the comments. We're on YouTube and LinkedIn right now. Thank you so much. We're going to get to those at the end. Please drop questions in there. We'd be glad to stick around and ask as long as we have to. So thank you so much for all the questions. So 7 of 12. How is sound measured in HVAC systems?
Yeah. So Tony, I lied. Sorry. When I mentioned that the sound pressure versus sound power was the most important topic, actually it's this topic right here, and we'll spend some considerable time talking about this. But again, if you take away anything from this presentation, it's this.
Two things.
No more
Two
lies.
things.
No more
Right.
lies. This is the most important topic in my eyes. So when we are discussing sound measurement criteria, HRI 20, and discussing sound measurement criteria in terms of heat pumps or ducted air moving and conditioning equipment. AHRI 260 is a standard adopted in 2001 for rating the ducted air moving and conditioning equipment. So prior to HRI 260, there was no standard for the evaluation of water source heat pump performance except whatever the manufacturers tested per their own internal procedures, making comparisons between two different similar models almost impossible. So with HRI 260 and a standardized test procedure and rating system, sound ratings are now usable by acousticians to estimate the resulting sound pressures of water source heat pump equipment in the buildings. There are primarily 3 applications to which units are rated, including casing radiated, ducted discharge, and ducted inlet. With casing radiated and ducted discharge applying most of the time, especially to the water source heat pump type of equipment. The other 2 applications typically not applied by manufacturers, which is basically that free inlet or the ducted inlet, what we talk about. So when we're comparing a particular manufacturer's sound data against any other brand, provided the technical guides must always express sound power levels in compliance with the HRI 260 to ensure how sound levels are actually measured. So we will spend a few minutes just kind of talking about the testing criteria. I won't get into the details of this. If you want, we can provide the testing standard or kind of go deeper into it at a different time. But to kind of move this along, I'll just touch on each one. So there, HRI dictates the requirement of a room or how the test is considered, how an equipment instruments are set up in that specific room, how a manufacturer is supposed to do the calculations driven from their test data, and also how should the sound rating be published as well. So HRI 260 will dictate that, and they have the latest basically publication in 2017. So in water source heat pump side, the criteria that we use is the reverberation room method. Reverberation room tests are conducted using the comparison method and a calibrated reference sound source as well. We'll talk a little bit more deeper. We'll talk deeper dive into the reverberation room later on, but it is a large room with highly reflective walls, ceilings, and the floor. The reverberation time of such a room is very long, and the longer it is, the more accurate the measurement. Uh, so talking about the test setup, and equipment location, the duct setup, static pressure taps, instrumentation, all of that is dictated by the HRI. Calculations are done per the standard HRI 220, and they are supposed to list them in the Octave Band sound pressure level rating system. And the sound ratings, which we'll just talk about in a second, is I'll go into how they should be published. So let's talk a little bit about how, before we look into that sound data itself, let's look at casing radiated and ducted discharge and just make sure that we explain what each one actually represent as well. So when measuring the sound, casing radiated sound power represents the sound a person would hear if they were standing directly in front of the HVAC unit. This is often considered as the third most dominant sound path after outlet and inlet sounds. The casing radiated sound power will depend on many factors, including the material type and thickness in a space, and the quality of material construction, internal components such as blowers or fans, electric motor and drives, vibration isolation of any blowers or fan as well. The ducted discharge on the other side is the worst case scenario and will provide the most airflow noise. The ducted discharge is a result of the sound energy that is focused into the ducts itself. Oftentimes in office buildings, a building like ours in Watertown, where we do not have an insulation built in between the wall and between us and the HVAC system, the ducts are right above me, and it is focused. So the sound coming out of the diffusers are directly impacting me. So that's what ducted discharge test is supposed to show. Oftentimes these ducts are located, they can cause a lot of sound complaints and will generate a lot of sound complaints. So that's why a manufacturer should be listing that information. Okay, so hopefully that makes sense, but let's review and understand how a sound data should be, listed, or what basically HRI standard sound data actually looks like. So in this, what you're seeing, and we don't need to get into the details of the sound itself. So I'll just kind of provide an overview of this. This is basically our newest model Whisper Quiet heat pump QV, which is going to be hitting the market in a couple months. And we list the sound data for that per the HRI 260-217. So we'll go through this and show what is supposed to be shown in regards to the sound data. So first, there you go. Okay, so first, any sound data or published sound data, especially for the heat pump, such as water source heat pump, should have a label dictating the casing radiated sound power or ducted discharge sound power. Then it should be listing the baseline measurements, if they have any, and what is the units of the sound measurement that they're listed. So in this case, we're listing 10 to the power of 12 watts, or 10 to the power of negative 12 watts, or 1 picowatts. So that should be listed. Next, what you will see is the units or the mode of operation for that specific heat pump. So per HRI, you're required to provide the cooling data, the heating data, and the fan data as well. So all combined sound sources data should be published in your publication. Then you should also have Octave Band listed. So per HRI 260-2017, you're supposed to put 63 Hertz, 125 Hertz, 250, or the Octave Band 1, 2, 3, 4, all the way up till 8. Per the older HRI standards, that was not a requirement. So a manufacturer needs to comply with the latest requirement. So that's what it will show, all the sound levels at various different frequencies. Okay, and then finally, it needs to provide the overall data in dBA for that specific unit as well. So the dBA value, as we talked, this is the A-weighted, where the sound levels are filtered to remove any impurities or anything that may affect the human hearing levels. So that's what we are showing for a specific model. So hopefully that's clear.
Okay, great. Thank you, Shaz. Okay, so question 8 of 12. So how do we calculate sound pressure from sound power?
Yeah.
Talk about that for a minute.
Absolutely. And this is something that we, as I mentioned previously, it's not really, it's not simple for us to calculate that sound pressure from sound power. But, we can just talk about how a sound is disseminated into the source and how we can perceive that, or how we can use that to basically get an estimated sound pressure level. So if the source of a sound is smaller than the wavelength of the sound it will emit, it can be represented by a point source. It will then tend to radiate sound equally in all directions in a spherical symmetry, with air particles moving back and forth as the wave expands outward. The point source model is a good approximation for the sound field radiated and the sound pressure level. From an ideal point source, it falls at the rate of about 6 decibels per distance doubled. So as a distance double, it will reduce by about 6 decibels. Sound from a line source, it generates and spreads cylindrically, meaning that for every doubling of distance, the sound energy is spread across double the area, and the sound intensity will halve as well. With the noise line source, the sound pressure level falls at the rate of 3 dB per distance double. Examples of a noise line source could include compressor piping, a train, or even a busy road, but in relationship to a piece of HVAC equipment, duct breakout, or noise transmitted through the walls of ducts into surrounding cavities. Let's look at the last one, the sound from the plane source. It radiates energy from a plane into a space, such as noise transmission through a wall. The surface itself radiates the sound into the space. An example of that is in relationship to a piece of HVAC equipment would be sound transmission through a wall separating a mechanical room from the conditioned space itself. Okay. Let me also show you, how we will be calculating a little bit. Again, this is just an estimation, but in terms of an HVAC, in the HVAC industry, it is we've developed a simplified model based on the source path receiver, where the source of the noise is basically the source of the sound, the path that it conveys, the path conveying the sound waves, and the receiver that hears that sound. So also remember, sound waves always transfer uniformly in a spherical manner from a point source. So also remember, the sound pressure level will decrease as a function of distance. So this is only applicable in an open field where zero reflections are present, and sound will travel from the same source towards the listener across an open area or space. It is always most efficient to eliminate noise at the source, followed by modifying the path if the source cannot be made quieter. And finally, instituting changes made by the receiver to avoid unwanted noise. Over to you, Tony.
Okay, great. Thank you, Shaz. And we're going to turn it over to Phil. I'm going to unmute you. You are unmuted. And question 9, Phil's going to talk about what causes sound in HVAC units. So very important to understand that. That's for sure.
All right. Thank you, Tony. Okay, so when we're focusing on the primary contributors of sound in HVAC systems, what we have to do is realize that dynamic power is used to move the air and the refrigerant in the system itself. So this causes sounds, and vibrations coming from the unit. So HVAC designers then always are going to have to deal with not only the unit's sound and vibration, but also the pitch and the loudness. Pitch is the change in hertz or frequency, while loudness is simply the change measured in decibels, which we've talked about, which is simply a quantifiable amount in a test chamber. The pitch depends on the frequency, and the loudness depends on the amplitude of the sound waves coming from the unit. So simply put, as loudness increases, pitch decreases, and vice versa. Okay, so remember that when we talk about water source heat pumps, the primary contributors are always going to be the compressor and the blower, or some people call it the fan. And of course, these sounds, these devices cause an effect on the listener to some degree. In fact, sometimes it's a lot of degree. So here we see a range of an example of 4 different types of equipment. So here you see a packaged water source heat pump. Some of you are familiar also with what we refer to as a vertical stack, or a mini split, a wall hanger is what I would always call those. Or even you can have an above the ceiling type of device as well that's ducted or unducted. So these are basically all of these are equipment in 2-ton size, and it indicates a relative sound power for each type of machine I show here in decibels. The typical range of these applications, all 4 of them, is between 2 and 4 kilohertz, or basically 2,000 to 4,000 hertz. We talk about secondary contributors also. There are many out there that emanate sounds that emanate from an HVAC unit, in this case a water source heat pump, and or system during operation. So we always have to consider the location of the equipment itself, because that can cause the sound to change based on the nearness to the other surfaces in that space or the components. So sound is distributed from the ductwork itself as the air moves through it. So these air movement sounds cause duct breakout noise we referred to earlier, or simply sounds that are escaping through minor holes or openings in the ductwork, really no matter how well they were fabricated or insulated. Additionally, any air distribution device that will provide sound as well, especially, of course, from supplier outlets or grills, people call them diffusers, registers. Well, all of those are dependent on their specific design and their placement. Often there's even a minor sound distributed from return air grills, or grills as some people call them as well. We talk about the room construction and layout that we referred to earlier. Other secondary sound contributors for HVAC equipment include the actual surfaces in the conditioned space as they reflect the sound waves. So these reflective surfaces should be considered always in the design phase. Any hard surface will cause a high sound reflection and a low sound absorption. So this could include things like construction additions like hardwood floors, wall boards, or even hard ceilings. Conversely, soft surfaces provide low sound reflection and high sound absorption. And that means including features like additions of carpeted floors, any type of wall hanging, or acoustic ceiling tiles. So then the question comes, go ahead.
Nope, go ahead.
No, I think it's over to you.
It's Shaz. Go ahead.
All right. Thank you, Phil. Turning it over to Shaz, and he's going to talk about question 10 of 12. So thank you all so much for sticking with us. We're getting right through this thing, and this is great information, guys, and I so appreciate it. So, okay, what are the recommendations to reduce sound? Good question.
Yeah. So first, I'll talk about the water source heat pump side, and I'll hand it over to Phil to talk about external factors as well, or any HVAC equipment which actually has a compressor or the blower. So what we are looking to do is we're looking to isolate and insulate any vibrating components. So we need to make sure that any of those components that will cause that, which is a primary contributor, which Phil alluded to earlier. In this case, we're talking about a compressor and a fan housing. We want to make sure that those get isolated. So on the right side, what you're seeing is a compressor, which is encapsulated and also insulated as well. So we try to make sure that from all sides, top, left, right, it has prevention or some type of insulation built in to basically trap the sound coming out of the unit itself. On the left, what you'll see is a blower housing. In this case, the picture that we're showing is like a hubless blower housing, where a control, which is actually generally placed in the blower housing itself, is placed outside. And that because inside the housing is where there's it can cause a lot of vibration. So what we make sure is if you're putting that control on the side, it will eliminate or isolate that vibration source separately. Also insulating that. So you will see, a black, picture or image around it, which is basically showing like it's insulated as well. So any sound coming out of the unit itself, it's basically attenuated to the maximum capability. Phil, would you like to talk about the duct side of it or the room acoustics?
Reducing sound from a ducted system. So these could include things like, but they're not limited to, canvas isolation duct connectors are often used at the unit. They put them in both the supply and return duct connections. People also apply internal duct lining materials to the ductwork. Sometimes they install 90-degree elbows in the supply discharge ductwork that comes from the unit. They add turning vanes to ductworks at elbows and sometimes at T's. They add short flex duct sections to the rigid ductwork at the supplier boots. And sometimes they even install air balancing hand-controlled dampers in the runouts near the main supplier air trunk to basically help you hand damper the air and the noise. So what we see is the addition of any or all of these type of recommended components will have some effect and reduce the sound considerably that is being delivered to the conditioned space. So all of them are highly recommended to consider. Thank you.
All right. Thank you, Phil and Shaz. Okay, so yeah, this is all good stuff, and it's so much easier to attenuate when you start with a very quiet unit to begin with. So that's my 2 cents after 25 years. Make sure the unit's not very loud to begin with. Okay, so question 11 of 12. What are the different types of sound testing facilities? And I know for me, this is really confusing, and Shaz talked to me a little bit about this yesterday, so hope you find this interesting. Go ahead, Shaz.
Yeah. So, in terms of room testing facilities, and we're coming up with a video to kind of showcase that a little bit more. Sorry, just 1 second. Yeah, so testing facilities, and basically when we're testing the HVAC equipment, the industry standard is basically to use a reverberation room. And as we talked about earlier, that's the AHRI standard as well. We have the similar type of testing facilities in our Florida factory. The reverberation room is designed to create or generate a sound field opposite of anechoic chamber, and I'll talk to that. It is the reverberation room. It's a sound. Allows us to create a sound absorption in the room, which is minimized using the specifically constructed walls. The testing in this type of room is conducted for both the casing radiated and ducted discharge for all types of HVAC unit. It helps to measure the sound power of a source and measurement of the absorption coefficient of a material as well. We spoke to the room setup as well. So there in the reverberation room gives us the ability to set up microphones, different pressure sensors, temperature sensors. So, there is a specific type of room setup dictated by HRI. And, in very short future, we'll have a video kind of showcasing various different types of sound facility rooms as well. On the in terms of research and development, what Bosch has developed is basically a state-of-the-art sound test facility, which is a semi-anechoic chamber. I say semi-anechoic chamber because a full anechoic chamber has a floor with springs built into it as well to make sure that it really provides, the most sound attenuation possible and clears out any filtration that's needed. So, but in this case, we'll talk about the semi-anechoic chamber. This chamber is shielded by, polyethylene foam panels, and they are, basically it's all around the room, as you can see in the image as well. These are it's in the shape of some cones. So these are acts as absorbent, which together prevents any sound reflection coming into the room itself. This also makes the chamber a free field environment for testing sound emanating from an equipment without any interference or the reflection. The sound levels from the radiating sound source will, like we talked about the point source, it will decrease by 6 decibels for each doubling of distance in these chambers. In this case, again, we measure sound pressure levels generally without any kind of disturbance or associated, and really allows us to create an equipment that's and calculate its exact sound power levels and pressure levels as well. So it's just a very helicopter view of some of the testing facilities that are utilized in HVAC.
Thank you, Shaz. Very good stuff, and that's a pretty impressive looking facility you guys have there. So thank you very much. And so last question or example. So Phil is going to give us some real life applications showing steps we can use to mitigate noise. So you are unmuted, Phil. Take it away.
All right. Thank you so much, Tony. All right, everyone. So when we talk about dBA, of course, that is a basic measurement we've referred to several times. But we talk about HVAC specifications, we really focus more on the NC value. So the maximum acceptable sound level in any given space is typically specified by a consulting engineer. So in order to ensure that the sound pressure that's ultimately heard by the listener in the space is below the maximum level, that sound pressure of the selected equipment, the characteristics of the space it's in, and the distance to the listener themselves are used to determine how well that sound is then transmitted or attenuated from the source through the various paths ultimately to the listener. The first table in this example simply shows the simulated data after taking into account the characteristics of the space and again the distance to the listener. We first plot the pressure levels on the NC curve, then we find the highest level at the 125 Hertz band where the purple line touches the NC 45 curve. What that does, it gives us an NC of 45. We can also find this on the table by looking for the highest NC value in any one octave band. All right, we're going to look at some cases now. So we'll look at this first case, and basically this is a school with a 2.5 ton unit, and we'll see how the construction changes the sound pressure in the space. So in the first case, we have a typical school classroom assumed with dimensions of 25 by 25 by 12 with a terrazzo floor and average construction, which also includes a few acoustical leaks and or visible holes. We're assuming a 10 by 10 duct size, inch by inch, with a 25-foot length as a trunk. We also assume a standard horizontal unit that's operating in the cooling mode with the blower set on high speed. So lastly, we are assuming concrete block walls, which are fairly common for schools nowadays, with mineral fiber ceiling panels, and the occupant is at least 5 feet away from the ceiling, the students. We take the sound power levels of the equipment and we subtract or we add the attenuation or propagation effects of the construction materials from it. And what we calculate is the sound pressure levels that the student actually hears. Then we simply apply the NC decibel filter to arrive at the final NC level. In this particular case, our handy sound calculator gives us an NC of 45 with a dBA of 44. This also, by the way, includes duct losses. So what we see here in this example is that NC 45 is really pretty high for a classroom. Typically, we would like to see a specification of around 25 to 30 NC with a maximum of 35. All right, that's the first one. Now we'll go to case 2. In case 2, we add the extra quiet options that most factories offer as options. Some of them are standard features that would include a compressor blanket and even closed cell foam insulation to the particular unit. So here we have the same unit that we did in the previous example, but we added these extra quiet options is what they're often referred to. And we see very minimal, if any type of difference, really only 1 decibel less, which really is barely perceptible at all. And we also simply arrive at the same NC, which is 45. So that doesn't speak very highly of compressor blankets and closed cell foam insulation. All right, now we'll look at the third case. So what we do now is we refer to this particular example as a whisper quiet or enhanced unit that Shaz discussed with added insulation and containment around the blower and the compressor compartments. So what happens here is we're changing to this concept, and it makes a huge difference. Suddenly, we went from an NC 45 to an NC 35, and the dBA dropped from 43 to 39, clearly indicating, really some good results from these particular innovations that were applied. Lastly, we'll look at case 4. And finally, in this one, what we've done is we've taken this whisper quiet type of construction and unit that we just mentioned, and we simply changed, in addition to the machine being contained around the compressor and the blower, we actually changed the classroom wall to utilize 2x4 construction and 2-inch 3-pound per cubic foot fiberglass insulation instead of the simple painted concrete block. So what we find is the fiberglass walls now help considerably, as now we get an NC of 25 rather than 35, even in the previous example. So in review, we've looked at a few of the more common sound ratings, discussing how material can act to absorb or simply reflect the sound more than others. And we also discussed in our case studies how a design engineer could do a rough estimation of the resulting sound pressure by having the unit sound data and knowing a few things about the construction of the space. Thank you, Tony.
Thank you. Man, that was some good real life stuff there. Thank you so much. So that was the 12 questions and 12 answers. So thank you guys for providing that information. And I know for me, like I've been in the industry for about 25 years, and I go through these phases where I pay real close attention to acoustics. They're usually just after I had a major problem. And then I kind of slack off and it gets in the back of my mind, and then I have a problem again. And I'm like, so it keeps me forefront in the issue. And I know that for me, it's way easier to fix these problems on paper before the unit's installed than after the fact, going back and having to fix a job it needs some attenuation. Attention is it's painful, it's stressful for everybody. It's usually expensive, and it's so much easier to do that up front. So thank you guys. That was an amazing presentation, and thank you all for watching. Please don't leave quite yet. I'm going to post the link for the PDH event here on LinkedIn and YouTube. Just click on that, take the quiz. If you get stuck or have any questions, you can email me. I'll put my email in there as well. It's tmormino@insightUSA.com. You don't have to write that down. I'll put it in there. So we got tons of questions. Please stick around. If you have to go, thank you for watching. If you're on YouTube, please subscribe to our YouTube channel. If you're on YouTube or LinkedIn, please like this presentation and give these guys a virtual hand of applause by liking what you saw here today. It means so much to us, and it helps us a lot when we have that engagement. So thank you. So I'm going to go ahead and do you guys have any last closing statements you'd like to mention before we start reading the questions and stuff?
Yes, sir, I would. This is Phil. In conclusion, I want to say this. Sound power, of course, is always going to emanate from the sound source. So today, in this case, we're talking about HVAC equipment. So remember, the sound power is a result of the testing procedures that, as Shaz indicated, are based on AHRI 260. So the resulting sound pressure will be measured at the occupant of the room, representing the actual resulting noise level as it approaches them. Sound pressure levels for a given room can be predicted using acoustical equations to estimate noise levels. Given the data, the noise performance can be estimated for HVAC equipment and commercial structures using standard acoustical engineering methods. So then the sound levels can be compared manufacturer to manufacturer and then predicted, resulting in innovative changes and improvements to equipment. Thank you so much for your time and attention.
Thank you, Phil. Shaz, any closing comments, or you want me to open up the questions here? Or?
No, I think Phil covered it really well. So I think we can get to the questions on this side.
Okay, great. So let's see here. I'm going to start at the top and go down. We got a bunch of stuff here. So, okay. Sounds great. Coming through loud and clear. Sounds excellent. Good on YouTube. Thank you, Sean. Andrew Cook, PE, was asking how to get his CEUs, and I just posted that in the chat, so it's a good question. There's a short quiz. If you get stuck or have any issues, I posted my email too, so save a copy of the link that I posted in the chat and save a copy of my email in case you get stuck. Email me. I'm glad to help. Let's see. David Lopes, I hope I'm saying that right, says everything's looking good. Jeff Elliott, thank you. Ron McLaughlin. Sean Frank says, good afternoon, gentlemen. Thank you, Sean. Aaron Coble says, awesome, guys. So if you want me to read your comment, make sure to put something really positive like that in there, and I'll make sure to read it every time. Will handouts of this session be available? Actually, no, I don't think we have any handouts prepared, but you can rewatch it on LinkedIn or on our YouTube channel. Insight Partners, HVAC TV. Go check that out. Bernie Nider, good morning to you too. Let's see here. Mark Murray, thank you to our partners at Bosch for supporting all of us at Insight Partners. So Mark is our president. So he says, thank you guys so much for doing what you're doing.
Yep.
And we do appreciate it. So Josh Eberly, PE, says, go Gators. Okay. All right, Josh. Lewis Palacios, I'm probably butchering that name. I'm sorry. Good morning. Thanks for the time. Hakeem Bailey says, sounds good. Justin Ware. Okay, yeah. So these are some comments about not being able to hear the example. I'm going to skip over those. We already talked about that.
Yeah.
We'll work on that. We worked on that so much. We thought we had it down. We apologize about that. All right, let me get to some questions here. Okay, so Mike Millard or Millard, it would probably be covered, but I'm interested in the effect of air in hydronic systems on sound levels. Air in hydronic systems? Any thoughts on that?
I think we didn't really cover that topic, right? We basically covered some of in terms of the air side of the equipment, but that's an interesting topic to talk about from our hydronic systems that we offer at Bosch as well. But, something that I haven't looked into, but I think that was not the topic that we covered on this, but it's definitely will have a strong impact. And I think it's something to consider, which I haven't really thought about too much. Phil, do you have any comments on that?
To some extent, a water source heat pump, it's not the classical hydronic system, but it is hydronic because it has water in it. So we do incorporate that sound effect as it travels to the coaxial coils and so forth. So that part of it is actually involved in the ENC calculations to some extent. But as Shaz indicated, not for like other type of hydronic systems, which we could investigate.
Okay. Thank you, guys. LinkedIn user, the name's not showing up. I apologize. Does sound frequency affect the hearing thresholds?
Yeah, and I think it's actually addressed right in the next chat as well. But and I mentioned that as well very briefly. It's between 20 hertz and 16,000 hertz. So that's the 16,000 hertz is a threshold of what human can endure. So frequency and basically the sound pressure levels will kind of affect as to how we can, what our human ear can take. As we know, probably a jet engine is basically the level where our ears start to kind of get affected, and we feel the pain as well. And I think also per our age, as we get older, our thresholds kind of start to shrink a little bit as well. So very well addressed in the chat.
Yeah, and Ian Bondsma, hope I'm saying that name right, has said the exact same thing. So thank you, Ian, for helping us out. We appreciate it. So how is it possible to take a correct evaluation of the necessary acoustics of a building? Any comments on that? How is it possible to take an evaluation of the necessary acoustics for a building?
They'd have to do sound tests for the structure itself. We're typically focused on equipment that is going into the structure. So you're talking a little bit more outside the area of our expertise. We're talking about HVAC equipment. I would assume that sound companies could come in and evaluate sounds in different types of parts of the structure based on the actual size and shape and what's in the room itself.
Yeah. And I think what we alluded to in our case study sort of is a theoretical example of that, where we are calculating the NC values, or an engineer basically provides a theoretical case, NC values for any given room based on the constructions, the windows, all the acoustical, nuisances in any given building. So that's how they're calculating it. It is very difficult to actually get the exact sound pressure levels at every single point, but generally engineers and manufacturers just get an estimated idea and do theoretical examples. But I know the acousticians, especially in the West Coast area, they go out to the buildings and actually measure that as well in terms of performance. But yeah.
Yep. And if you need a study done, post it in the chat here. And there's a lot of people who've seen this and will see it. Maybe someone can reach out to you. So, okay. So, Jeff Elliott, is there a minimum length for the short flex section?
Most of my life, I used 3 feet, but I never found a standard. There may be a local code and ordinances for flex duct. So I've seen people use 3-foot sections, 6-foot sections. The entire run was flex duct hooked to a metal trunk. So it varies all over the country. Some places dictate that. Most places I've seen in SMACNA and so forth, 3 feet was about the average.
Yeah. Okay, that makes sense. Thank you, Jeff, for your question. Mike Gable, can a duct obstruction like an MVD create additional noise? Assuming that's a damper.
Yeah, motorized volume damper, that of course could, because as pressure increases, the noise would elevate, pitch would change, amplitude would change, and so forth. So that would have to be considered in the test. Just like I mentioned, putting in hand dampers in the runs near the supply trunk, that also has to be considered too. So anything that is put in the air path would have to be incorporated into the sound test. Has an effect on it.
Right. Okay. Thank you, Phil. And Bob Moore says, "Tell Phil Raines hello." So I sounds like you got a buddy on here.
Thank you, Bob Moore. Hello to you.
That's always so much fun. Okay, so Patrick Roberts, do you look at specific frequencies and resonance?
Yeah, as we mentioned and we showed, for as an HVAC manufacturer, we are looking at octave band 1 through 8, which is all various different frequencies, right? Some example of that is values like we say 63 hertz, but it's basically all of that range all the way up to 125. 90 hertz. I think that was the value on that. But we take all ranges and we show sound data at all ranges from 63 all the way up to 8,000 hertz from the HVAC side, because that's where most of our equipment will be playing, the sound will be noticed. So at various different frequencies, you're going to hear various different sound levels as well, and they're going to be perceived differently, as we showed in some of the charts that was displayed in the presentation. Hope that answers.
Okay, yes, very good. Thank you. So we have another question here. Any ideas to reduce breakout noise from fan coil units and air handling units? Breakout noise.
Most likely be more insulation, sealant or things like that I've used in the past. External duct wrap, whatever. It depends on the type of duct system you have. Anytime I have a hole in the duct, I'm going to have duct breakout noise, no matter what. No matter how well I insulate them or whatever, there's always going to be some perceptible air loss or sound loss. So the tighter, the more integrity you can have around or in the duct, the less you will have.
Makes perfect sense. So next question, is a water source heat pump louder in cooling or heating mode? I'm curious to hear the answer to that one.
I would think that in my life, in cooling, I always heard more noise than I did in heating. And that's just basically the fact that we have moisture-laden air that is collecting on the coil and condensing out, which changes the static pressure. It also reduces the CFM, per ton that we're moving. And in heating, we have dry heat and, very little relative humidity to deal with, no wet bulb. So sound goes up in cooling almost always, to me.
Okay. You guys would know, that's for sure. Okay, I'm just looking through the comments here. Okay, so Josh Poole has a question. Is mineral fiber insulation more effective at attenuating sound versus polyurethane spray foam?
I haven't had any experience with that, but I would assume because of the properties of the foam, it probably work is a little better. That may be an error on my side, but I'd have to look into that. But just reading spec data, it tends to coat and dry and thicken up. It's used quite frequently to insulate houses and buildings and so forth. So I'm sure it has some effect on reducing the sound.
Okay. That's a tough one. Okay, so Steve Clankson. Steve is one of our top guys here at Insight. And thank you, Steve. Always generous making comments. So in performing the tests in the field on installed equipment, how do you compensate for ambient noise that is louder than the equipment? Can the data be extrapolated or interpolated and still be accurate? Very, very good question.
Shaz, that gets into the chambers, and the way I look at the chambers, you have two different styles. One, no noise is transmitted. The other one is you're receiving the noise. So if you have ambient noise around it, in that chamber, we're not going to have ambient noise unless we introduce ambient noise into it and account for that. What are your thoughts?
Yeah, I mean, so the tests generally are done in a controlled environment, right? Like as you mentioned, the semi-anechoic chamber where there's basically no ambient noise added other than what is already existing, but the reverberation room have some ambient noise. So, but I think the question was in regards to the field on the installed equipment. How do you compensate for that? So that's something that I would have to look into a little bit more to see how we can compensate for that. So I would have to get back to Steve on this one for sure.
Got it. Thank you. Let me just look here. I think we have a few more. Lewis says, thank you so much. Great. We appreciate it. Bo Mixer. Oh, wow. Hi, Bo. He says, good stuff. Thanks, guys. Bo, I called on him. And when I was in Florida, this was a great presentation. Gerald Wendell says, it's a great presentation, especially when we think about the effect on noise on student living as well as patient stability and recovery. Yes, for sure.
Yep.
Mike Millard says, great presentation. Nick Nadu, great job. Syed says, thank you guys. A lot of thank yous and greats. Great presentation from, let's see, David Lopez. So awesome. I think I have all the questions there. I think we've answered all the questions. And before you go, thank you so much again. First of all, thank you to you guys at Bosch. You guys are amazing. This was a really, really good presentation. It'll live on our YouTube channel and here on LinkedIn, and going to serve a lot of people, educating them on HVAC acoustics. My contact information will be on the video description, no matter where you're watching this, either LinkedIn or YouTube. So you can contact me if you have any questions, have an application you want us to look at. Bosch is the experts, especially when it comes to water source heat pumps. So please keep us in mind for that. Reach out to us. And one more time, if you're still watching and haven't liked this video, please like it. Feel free to share it, comment if you will. We'll be going back and checking the comments. And please follow us on our YouTube channel, Insight Partners HVAC TV. And you can check out our new podcast where we will also post an audio version of this, which is called the Engineers HVAC Podcast, which is new for us and has been great. We've had a lot of fun with it, and we're going to start doing a lot more. So please come check it out. So thank you all so much for being here. Anything else we need to mention, guys? Or
no, thank you for having us, Tony. This was amazing. Yes, appreciate that.
My pleasure. Thank you so much.
Awesome, guys. So stick around. I'm going to end the stream, and thank you all so much again for watching.